Welcome to the Deep Dive. Today we're cutting straight to the heart of your computer's high-speed nervous system, PCI Express or PCIe.
That's right, the backbone.
Yeah, exactly. We've compiled some pretty deep technical dives into how PCIe makes sure data flows in the right sequence.
The ordering part.
And also how it maintains, rock-solid connections between your components. That second piece our sources called data link layer packets, or DLLPs.
Crucial stuff for link health.
Right. So our mission here is to unpack these maybe seemingly technical mechanisms and reveal why they're just essential for a stable, powerful machine. Wow. We want to offer insights that go, way beyond the spec sheet.
Sounds good. Let's get into it.
Okay, let's dive in. Starting with why the order of operations in PCIe, why does it even matter?
Well, think of PCIe as this incredibly sophisticated communication network, right? Inside your computer.
Okay.
And in any system like that, the timing, the sequence of messages, it's critical. I mean, imagine if your brain got sensory info all out of order.
Total confusion.
Yeah, exactly.
Yeah.
Catastrophic. And it's similar inside your computer. If data and commands arrive in the wrong order, you could get anything from, subtle software bugs, all the way up to complete system crashes, deadlocks.
Yeah.
Plus, a lot of software, it's very logic, relies on basic assumptions about the order hardware operations will actually execute in.
So it's not just if the data gets there, but when, relative to everything else.
Precisely.
Our sources really detailed this classic producer-consumer model in software. Can you maybe unpack how PCIe's ordering rules make that specific model work reliably?
Yeah, definitely. The producer-consumer model, it's a core design pattern. You have one part of the system, the producer, generating data, and another part, the consumer, processing it. And often they use shared memory as the go-between.
Right.
Now, a key part is the signaling. The producer has to reliably tell the consumer, hey, the data's ready. So, when my network card gets data off the internet and chucks it into memory, how does my CPU know it's safe to grab? That's a perfect example. The network card, the producer, writes the incoming data into, say, a specific memory buffer. Then, after that, it writes a little flag somewhere else in memory. That flag tells the CPU, the consumer, okay, data's complete. Go for it.
Gotcha.
And here's where PCIe ordering is absolutely vital. That flag must be written after all the data.
Right.
If somehow within the PCI fabric, that flag write managed to jump ahead of the data writes.
Oh, boy.
The CPU might see the flag, think the data is ready, and start processing garbage. Incomplete, corrupted info.
Yeah, that sounds like a recipe for digital chaos.
Yeah.
So what specific rule in PCIe stops the kind of mess with these fire and forget writes?
There's a fundamental hardware rule. PCI specifies that posted write TLPs, those are the transaction layer packets for these fire and forget things like R data and flag writes.
Okay, PLPs, got it.
Those posted writes are not allowed to pass other preceding posted write TLPs within the same traffic flow.
So they have to stay in line, basically.
Exactly. That hardware enforcement guarantees the sequence the software intended, like in our producer-consumer example, is maintained all the way through the fabric.
Okay.
It really shows how these seemingly low-level hardware rules are critical for supporting high-level software patterns.
That makes total sense, like ensuring the ingredients are on the counter before the chef starts cooking. Okay, now, our sources also mentioned deadlocks. How does PCIe ordering help prevent those system-halting nightmares?
Yes. This is where it gets interesting, kind of a balancing act, because while that strict ordering we just talked about is vital sometimes.
Like for the producer-consumer.
Right. Too much rigidity can actually cause other problems, like deadlocks. Imagine device A sends a read request to memory.
Okay, a read.
That's a non-posted request, meaning it needs an explicit response, a completion TLP, with the data.
Right, it's waiting for an answer.
Exactly. Now imagine device B wants to send a write request that's usually posted through the same switch or path, while A's read is still waiting for its completion. If writes were never allowed to pass reads, device B's write would just get stuck there, waiting behind A's read.
And that waiting game could lock things up.
Potentially, yes. A deadlock happens if, maybe due to some weird dependency, the completion for device A's read actually needs device B's write to finish first.
Oh, like a circular dependency.
Precisely. The read can't finish till the write happens, but the write is blocked by the read. Boom. System freeze.
Yikes, that sounds bad. So how does PCIe ordering specifically prevent that gridlock in a complex system?
There's a crucial counter rule. Posted requests, like that memory write from device B, must be allowed to pass non-posted requests, like the memory read from device A.
So they can jump the queue in that specific case.
Exactly. It's a deliberate exception designed to break that potential circular dependency. It keeps the system making progress, even if it means slightly relaxing the ordering between different types of transactions.
It really sounds like a very carefully thought out set of rules, balancing correctness and, well, keeping things moving.
It has to be.
So we've mentioned posted and non-posted requests, and you mentioned completions. Our materials dive into these three categories. Can you give us a clear rundown?
Absolutely. These three posted requests, P, non-posted requests, NP, and completion, CPLL, they're the fundamental building blocks. The ordering rules are all about how these three interact.
Okay, let's start with posted, the fire and forget ones.
Right. Posted requests, P, sender sends it, doesn't expect a direct reply. Think memory writes, message TLPs, they're optimized for throughput. Switches can buffer them.
Others.
Handled indirectly, usually at a higher level. Flow control for these uses specific credits. Posted header, PH, and posted data, PD credits.
Got it. Okay, non-posted.
Non-posted requests, NP, are the opposite. Sender always expects a completion TLP back.
Like the read example.
Exactly. Memory reads, I/O reads writes, config reads writes, atomic operations too. Here, reliability and confirmation are key. The sender puts a tag in the header.
The ID tag.
Yeah, to match the request with its eventual completion. Config writes, which set up devices, are NP to make absolutely sure they happen correctly and in order.
Makes sense.
Yeah.
And they have their own flow control.
Yep. Non-posted header, NPH, and non-posted data, NPD credits.
Okay. And finally, completions.
Completion, CPL, are just that. The responses to non-posted requests, sent by the device that fulfilled the request.
So they say success or error.
Right. And if it was a read, they carry the data back. They also have the tag to match the original request.
And flow control for these two.
You bet. Completion header, CPLH, and completion data, CPLD credits, keeps everything flowing smoothly.
Okay, so P is one way, NP is request response with a tag, CPL is the response.
Got it.
Our sources had this simplified ordering table. Kind of a cheat sheet.
Exactly. It visually summarizes the default rules for how these P, NP, and CPL transactions interact within the same traffic class and virtual channel.
Can we walk through that? It seems helpful.
Sure. Imagine the table. Rows are the first transaction arriving. Columns are the second transaction arriving. The entries say, yes, may pass, or no, must not pass.
PCIe simplified transaction ordering rules. Default behavior. First transaction arriving, P. Second arriving, NP, second arriving, CPL, second arriving, no, NP first, yes, no, CPL first, yes, no.
Okay, looking at it, first row, P arrives first. Everything else gets a no.
Right. That reinforces the strict ordering for posteds we talked about. Producer-consumer safety. Nothing overtakes an already in-flight posted right in the same flow.
Makes sense. Second row, NP arrives first.
Here, a later P can pass it. That's the yes. That's our deadlock avoidance rule in action.
Oh, okay.
But another NP or a CPL cannot pass to the first NP, so no for those.
Yeah.
Keeps related non-posted operations in sequence.
Got it. And the last row, CPL arrives first.
Then subsequent P and NP requests can pass it yes for both. This helps keep new work flowing, prevents old responses from blocking new, unrelated requests.
But completions can't pass other completions.
Correct.
Yeah.
No for CPL passing PPL. Maintains order for responses going back to the same requester.
Wow, okay. That table really does clarify the defaults. You see the strictness for posted, but also the deliberate exceptions, like posted passing non-posted, to prevent those deadlocks.
Exactly. It's a carefully tuned system.
Now, things get spicier, right? Our sources say this default order can actually be modified for performance. Why mess with these carefully designed rules?
That is an excellent question. Because sometimes those defaults, while safe, can create bottlenecks. Unnecessary waiting.
Like when?
Imagine transferring a huge file chopped into many independent data chunks. The default posted can't pass posted rule might force all those chunks through one by one.
Even if the application doesn't care about the exact order of the chunks.
Precisely. It could limit your overall throughput. So PCIe provides ways to selectively relax these rules when it's safe and beneficial to do so.
And those are relaxed ordering, our O and ID-based ordering.
Yeah, those are the main ones, yes.
Okay, let's tackle relaxed ordering first. What's the deal with RO? How does it speed things up?
Okay, relaxed ordering, RO. It's basically a flag, a bit in the TLP header. that the device sending the transaction can set.
A permission slip, kind of?
Yeah, sort of. Setting R01 on a posted request, like a memory write, gives it permission to bypass other posted request TLPs ahead of it in the same flow.
So it specifically breaks that posted can't pass posted rule we just nailed down.
Exactly. It allows switches more freedom to reorder those R01 writes to maybe fill gaps or optimize routing, improving throughput.
Does it affect non-posted or completions?
No, that's key. RO primarily affects posted passing posted. It's huge for things like high-performance computing, RDMA networking, intense GPU to GPU stuff.
Where you're just blasting tons of data.
Right. Lots of independent chunks. You mark the data packets with R01 so they can flow freely, maybe out of order. And then typically, you send one final synchronization write with R00. That final write won't pass anything, so it acts like a barrier, ensuring all the R01 data arrive before the receiver acts on it.
Clever. So you get the speed boost but maintain correctness at the end.
Precisely. You might even see environment variables or driver settings letting you tweak RO usage for certain devices.
Very interesting. Okay, so that's RO for letting transactions within a stream reorder. How does ID-based ordering, IDO, differ?
IDO, ID-based ordering, is another way to relax rules, but it's based on the source of the transaction, the requester ID, or RID.
Okay, so who sent it matters now.
Right. Each function or device has a unique RID. If a TLP has the IDO bit set to 1, it's allowed to pass preceding TLPs only if those preceding TLPs came from a different requester ID.
So stuff from device A can pass stuff from device B, but stuff from device A still stays ordered relative to other stuff from device A, assuming RO isn't also on, I guess.
You got it. It maintains order among TLPs from the same source within the same TCVC, but allows different sources to interleave more freely.
Where is that most useful?
Think traffic jams at switches. If a switch is handling traffic from multiple different devices downstream, IDO lets the traffic from one device flow past backed up traffic from another, preventing one slow device from blocking everyone else using that switch. It's also great for multifunction devices, single cards acting as multiple logical devices, each with its own RID.
So it keeps independent streams flowing independently through choke points.
Exactly. It improves overall system responsiveness when lots of things are talking at once. It's often considered pretty safe to just enable IDO broadly for devices sending traffic.
Okay, so putting it together, RO is more about letting chunks within a big transfer from one source reorder for throughput.
Yep.
While IDO is about letting traffic from different sources interleave better at aggregation points like switches.
That's a great summary. RO for bulk data flow, IDO for source-aware relaxation, and, PCIe keeps evolving. PCIe 6.1 introduced unordered I/O, UIO, which is an even bigger shift, but that's maybe a topic for another day.
Right, always more layers. Okay, this has been super insightful on the transaction layer side, ordering performance creaks. Let's shift gears now to the other critical piece from our sources, the data link layer and these DLLPs. This layer seems more focused on the immediate connection, right? Point to point.
Exactly. We're zooming in now. The data link layer isn't worried about the end-to-end journey of data like the transaction layer is. It's purely focused on the health and reliability of the direct link between two adjacent components, like between your CPU and a switch, or a switch and your graphics card.
So what are its main jobs down at that link level?
Think of it as the link's guardian. Its core functions are, number one, reliable TLP transport, making sure the TLPs we just discussed actually get across that one specific link without errors. That means error detection, sequence numbering, and retransmissions if needed.
Okay, reliability. What else?
Number two, flow control. Using that credit system we touched on, but managed at the link level with DLLPs to make sure the transmitter doesn't swamp the receiver's buffers on this link.
Prevents overflows. Got it.
3. Link power management. Coordinating entry and exit from low-power states like L0s or L1 to save energy when the link isn't busy.
Smart.
And 4, it plays a big role in link initialization and training, working with the physical layer to get the link up and running stably in the first place. It's really the foundation making sure that high-speed signaling actually works reliably.
And DLLPs, data link layer packets, are the tools it uses for all this.
Precisely. DLLPs are completely separate from TLPs. They're small, fixed-size packets generated and consumed only by the data link layers at each end of a single link.
They don't carry user data. They don't get routed through switches.
Nope. Strictly local traffic for managing that specific link's health and operation.
What's their structure like? You said small and fixed.
Yeah, designed for speed and low overhead.
Yeah.
Typically just 8 bytes on the wire. There's usually an 8-bit field saying what type of DLLP it is.
Okay.
Then maybe 16 bits of data specific to that type. And finally, a 16-bit CRC, the link CRC or LCRC, just for checking errors on the DLLP itself. Very simple, very efficient.
Makes sense for control messages. Okay, our sources listed several standard types. Now let's start with the acknowledgement ones. ACK and NAC. How do they guarantee TLP delivery?
These are absolutely fundamental for that reliable transport function. The transmitter's data link layer slaps a sequence number onto every TLP it sends out.
Okay.
The receiver's data link layer checks the TLP for errors using its own CRC, different from the DLLP's LCRC, and checks the sequence number. If it's all good, no errors, expected sequence.
It sends back an ACK.
Exactly. An acknowledgement DLLP and ACK. It basically says, yep, got everything up to sequence number X successfully. This lets the transmitter know those TLPs made it, and it can clear them from its retry buffer.
And if there is an error, bad CRC, wrong sequence number,
then the receiver sends back a negative acknowledgement DLLP and ACK. That tells the transmitter, whoa, something went wrong. You need to resend TLP number Y, or maybe a range of them.
So the transmitter replays them from its buffer.
Right. This constant ACK-NAC exchange ensures that, despite potential noise or glitches on the high-speed link, the TLPs get across reliably, link by link.
Okay, a solid handshake for data integrity at the link level. Now, what about flow-controlled DLLPs? Init FC1, Init FC2, Update FC. How do they stop buffer overflows?
Right, flow control. This is that credit system we mentioned, but managed via DLLPs. It prevents a fast sender from overwhelming a slower receiver's input buffers on this specific link.
And it tracks credits for different TLP types, headers, data?
Exactly, and per virtual channel, too. It's very granular. Credits for posted headers, posted data, non-posted headers, non-posted data, completion headers, completion data. 6 categories per VC.
Wow, okay. How does it start?
During link initialization, the two devices exchange Init FC1 and Init FC2 DLLPs. These basically advertise, here's how much buffer space, how many credits I have for each of those 6 categories on this VC.
So they declare their capacity.
Yep. The transmitter starts with 0 credits. It can only send a TLP of a certain type if it has received enough credits for that specific type, header or data for that VC, from the receiver.
And how does it get more credits?
As the receiver processes incoming TLPs and frees up buffer space, it sends back Update FC DLLPs.
Here are some credits back.
Exactly. An Update FC says, I'm giving you back X credits for, say, posted data on VC0. This replenishes the transmitter's pool, allowing it to send more.
That granularity seems crucial. Stops one type of backed up traffic from blocking everything else?
Precisely. It prevents head-of-line blocking on the link, ensuring that different traffic types can flow independently based on the available buffer space for each. It's key for efficiency and fairness.
Makes sense. Okay, then there were power management DLLPs. How do they help save watts?
These are the messengers for coordinating power state changes on the link. Things like L0's a quick, low-power active state, L1, L2, deeper sleep states.
How do they coordinate?
Devices exchange specific PM DLLPs like PM Arrow 1 or PM Request Stack to signal, hey, I want to go into L1, or are you ready to wake up? It ensures both sides of the link transition power states together, synchronously.
Does this work automatically, or does software control it?
Both, actually. These DLLPs support hardware-driven schemes like ASPM, where the link powers down automatically after inactivity, and software-directed power management, where the OS or drivers explicitly request state changes via the hardware.
Flexible. Okay, nearly there. 2 more specialized DLLPs mentioned, NOP and data link feature. What's their story?
NOP is simple, no operation. It's basically a placeholder, a filler packet.
Why send nothing?
It's mainly used during link training or recovery, like when waking up from L1. You need to send something validly formatted just to keep timing or synchronization going, even if there's no actual control info to send at that exact moment. So NOP, DLLP.
Okay, a keep alive and data link feature DLLP.
This one is for negotiation. PCIe has optional features at the data link layer. Devices use data link feature DLLPs to ask each other, hey, do you support optional feature X? And then agree whether to enable it.
Like what kind of features?
A common one is advertising support for more or fewer fast training sequences, FTS. More FTS patterns allow for a faster exit from the L0's power state, improving responsiveness, but maybe using slightly more power. So they negotiate.
Gotcha. So it sounds like while we focus on the big data transfers, this data link layer using all these different DLLPs is just constantly chattering away in the background, checking for errors, managing credits, coordinating power states, negotiating features, just keeping that physical connection humming along reliably.
Absolutely. It's an incredible amount of intricate, low-level communication that has to happen perfectly for the high-level stuff, the TLPs carrying your actual data, to work at all. PCI's performance and stability really hinge on this tight integration between the transaction layer's ordering rules and the data link layer's meticulous link management via DLLPs.
So wrapping this up, these seemingly, dry technical details about ordering rules and DLLP types, they aren't just academic. They're absolutely fundamental to the stability, the performance, the sheer functionality we expect from our computers constantly.
Couldn't have said it better myself.
Understanding this layer, even just a bit, gives you a much deeper appreciation for the complexity hidden beneath those seamless data transfers. And seeing how PCIe evolves with things like relaxed ordering, IDO, and looking ahead to UIO, it just shows this relentless push for more performance, more flexibility in how everything connects.
Exactly. And remember, this directly impacts everything you do: streaming, video, gaming, scientific computing. The speed and reliability comes from getting these fundamentals right.
That is a fantastic point. Okay, on that note, maybe a final thought for you, the listener, to mull over. Think about these principles we discussed: ordered communication, reliable connections, flow control, error handling. They're not just inside your computer, are they?
Good point.
Look at other complex systems, traffic control, supply chains, even just trying to have a coherent conversation. What are the ordering rules there? What are the DLLPs, those little background signals keeping things flowing? And what happens when they break down?
Yeah.
Maybe understanding a bit about how PCIe nails this down can give you a fresh lens to look at order and maybe sometimes chaos in the wider world. Something to think about. Thanks for joining us for this deep dive.